In today's session, we will take a beginner's take on reinforcement learning. So, after attending this meeting, one should go away with feeling that they have a basic understanding of RL or reinforcement learning, and also why it is going to be important in the agentic world, where agents are supposed to take autonomous their decisions on their own. A bit about me. I work as a senior data AI scientist, and I have put few models in production across traditional ML, RL, as well as Gen AI. I also review books for Manning publications in reinforcement learning. I have a master's in AI and ML. So this is what we will cover. So what is RL and why it matters for modern AI builders? How agentic AI and RL enables continuous improvement, and we will also discuss a few real world enterprise use cases. So when we talk about the scenarios, like a kid exploring a new game or a chatbot providing responses to a user, further, it can become as complex as landing Chandrayaan on Moon or uh, Autobot exploring the Earth by itself. So the characteristics, what we are seeing, which would be common here, is that the environment in many cases would be unknown. In some cases, it might be known, but in most of the cases, it would be unknown. Given a scenario in the environment, one must take a decision. This is also called as actions in the reinforcement in the world. Now, given an action or a decision which has been taken, it may lead to a positive or a negative outcome or experience. For example, when playing the Mario game for the first time, uh, one might get a negative reward too often because the game is unknown and we are trying to explore various scenarios. Also, it might happen that in many cases, the impact of the current decision might not be immediately known. So let's take an example of chess. We take a move, but we don't get instant feedback more often. It's just that we are changing positions, but it doesn't mean that we either take up opposition pieces. It can also happen that we get a feedback towards the very end, which are quite often in a gaming scenario where the character or the avatar in the game gets killed more often than not. Now let's take an example of a chatbot. In this case, what can happen is that if the chatbot responds in a way which is not relevant, the user might stop his interaction with the chatbot. Now, reinforcement learning. As a human being, we learn by interaction with our environment. That comes natural to us. Like I mentioned earlier, let's talk about a little person or a little kid playing in front of a video game, which he has never played. So what he will do is that he will interact with the console, do some random movements, and try to figure out as to what step of his leads to a reward or a penalty. So idea behind reinforcement learning is that we have an agent who will learn from an environment by interacting with it through trial and error. And on the process, he will receive rewards, which can be positive or negative, as a feedback for performing his actions. So what is RL? RL is a mathematical formulation to learning from interactions. It is learning about what to do, how to map an action to a particular scenario. So in the gaming example, the person or the kid playing can be termed as an agent. The console is an interaction which gives him a means to take an action, which could be left, right, jump, up, down, so on and so forth. And the game provides the environment to him. And based on his interaction, he can get a reward, which could be positive in nature or it could be negative in nature. So as a result of interaction with the environment, he finally learns a policy in his brain. So policy is that given an state, what is the best action to take so as to maximize the reward over the duration of our interaction. Let's talk about the fundamentals now. RL provides a framework which is called as Markov decision process. So in this, there are two components, the agent and the environment. Environments provide a scenario to the agent, and the agent will take certain action on it. And based on that action, he might get a positive reward, which is positive reinforcement, or a negative reward, which is a negative reinforcement. So it starts with the environment presenting a state to the agent taking an action given that state. Due to the action, the environment presents a reward or a reinforcement, which could be positive or negative in nature to the agent. Post this, depending on the action taking, environment might present another state to it, to the agent. And the agent would take another action, leading to another reward for the user. So MDP is a formalization of sequential decision making. We are calling it sequential because the decisions taken today or at this point of time influences the state presented to the user, which further influences the action taken. So it is a long term of actions, reward, state loop, or state action reward loop, which is also called as SARSA. So let's briefly talk about the terms. And the terms are observation and state space. Observation or state is the information the agent gets from the environment. So for example, in the case of a video game, it could be a frame, or in the case of a trading agent, it could be a value of a certain stock. Now, we can think of a state which captures everything which matters for decision making. So in the case of, it could be, for example, inventory levels. If we are trying to do a supply chain management, it could be active custom orders, available trucks, production schedules, cash outflow status, depending on the specific problem we are solving. Now, there is a differentiation between observation and state. State means we have a complete description of the state of the world. For example, in the chessboard, we know where each and every pawn is. We have a fully observed environment in this case. When we talk about observation, there is a partial description of the state. We just see a frame of the entire environment. And this is also called as partially observed environment. Now, when we talk about action space, these are the list of possible actions which a agent can take given a scenario. And actions are also described. It could be discrete. It means that I have a finite number of possible actions I can take. For example, in video game, one can do left, right, up, or down. We can also have an action space which is continuous in the sense that the possible action is infinite. So this example could be a self-driving car, where there is a possibility to turn the car in infinite number of angles, or honk, or apply brake, or so on and so forth. When you talk about task type means interaction. How do we interact with the environment and how long we interact with the environment? So it could be episodic in the sense when we play a game, a person can run out of lives or they can be killed. So these are known as episodic. There is an end to it. In the continuous task type, there's a task which go on forever. For example, we are monitoring the stock market. So there is no terminal state for it. Let's talk about the reward hypothesis, which is the central idea of reinforcement learning. So as in real life, we kind of perform actions so as to achieve a goal. A goal is a representation of a reward in life. and we tend to work towards that goal. So the central idea of reinforcement learning is that it works towards the maximization of expected return or expected reward. And the agents learns to behave in such a way so as to maximize the reward, cumulative reward. Now, when we talk about rewards, there is also a concept called as discounting. So what does discounting mean? What it means is that the immediate reward I achieve now is more important the reward which might come 2 steps down the task or our interaction with the environment. So we tend to discount those rewards, and this is the discounting term over there. So we discount a term called as gamma, and this is called a discounted reward or discount rate. The other term is exploit. So we can explore various scenarios in our environment. Should I explore or should I take a known path? So for example, if I love biryani, should I eat biryani today as well? Or do I go and explore a new recipe, which eventually might either be turned out to be something I don't like or something I enjoy a lot. So this is known as exploration. Going with the biryani would be known as exploitation because I'm already taking a path which I have explored earlier, and there is a guaranteed reward over there. Now let's talk about environment. So the environment is what the agent interacts, and it could be of 3 types. The first one could be like a deterministic, where we know if we have a 3 stage. So consider the scenario where a person who has bought a basic plan, he might go to buy a pro plan, or he can cancel a plan. So these are the 3 stages: basic plan, buy pro, cancel plan. Now, when we talk about deterministic, we know for sure that given a basic installation, there is 100% chance that he will go to buy a pro, and there is a 100% chance that he might go and cancel. So the state transition from one state to another is known to be 100%. Now, there is another type of environment which are stochastic with known transitions. So given 3 states, we know what could be the possible transitions from one state to the other. So in this case, if a user has installed a basic plan, there is a 30% chance that they can go and cancel the plan, and so on. So forth. There is another type of environment which is known as stochastic environment with unknown transitions. So here, do we know this? Though we know the states, we don't know that the probability with which it can transition from one state to another. So this is known as a model-free environment. So we don't have a model of the environment available. We don't know about the environment. The stochastic one is known as model-based environment. So there is a model of the environment with us, and we know the probability with which various transitions can be made. There is another concept called as Markov chain. So what it means is that a state today depends on the state I dealt with in the past. So it's more like the condition I am today in my life is a function of the states what I was presented earlier. Markov decision process is a variations of is a mathematical formulation where though we have a state, we allow the user to intervene in the state change by performing some action, and as a result of action, it gets a reward. So what MDP provides us is a a mathematical formulation as to how to act when facing uncertainty. So uncertainty is presented to us by the environment, and it also provides a method as to how to measure the consequences of these actions. We have another term called as policy. So policy is what the agent learns by interacting with the environment in a state, action, reward, next state, next action, next reward manner. So given a state, the goal of the agent is to train itself with a policy so as to take an best action leading to the maximization of the reward. So the final goal is to learn the optimum policy through training. So let's talk about the RL characteristics. So here we are seeing that there is no supervision. When we say action, take a action, there is no supervision in the form saying that that action is bad or should not be taken. What one is presented is with a reward signal. So the reward signal does not imply that this is the best action for the overall journey in that episode. What is implied is that given that state, if you take this action, it's a positive step towards the long-term horizon. Here, decision making is sequential. We take a decision, we are presented another state, we take another decision till we reach the end of the episode. Scenario phase is dependent on the earlier decision. So the state presented to us is based on the action we take. So given a state, if we have 4 actions, if we take a different one, we will be presented with a different state. The feedback at times isn't prompt but delayed. So I might take action and I might not receive any kind of reward uh, for taking the action. For example, in the example of a chess where I just moved the pawn, the time horizon is of importance in the reinforcement learning problems. So it is a long-term planning problem. It's not one-off. It has a long time horizon. Now, when we talk about agentic AI, one of the things right now mentioned is the ability of the agents to take autonomous decision. Right now, there are several approaches like relying on test time compute in the terms of uh, thinking at the time of inference. And these are in context of LLMs, which are basically textual models. But the general paradigm in autonomous thinking is that tell me what to do and not how to do. I will figure it out. So on the right hand side, we are seeing an image, and this is Jan LeCun's view of how we can go about and achieve autonomous behavior. So what we can see here is that if we see the globe over here, this is a representation of an environment. It presents a perception, which is a state, and based on the state, the agent, what is being referred to as an actor, takes an action, which kind of leads to a cost. There are a few other elements like critic, world model, short-term memory, configurator, which are additions to achieving it. But the thing to note is this section is very much model like how RL is defined in the form of MDPs. So why use the RL for the agentic scenario? Because it's closely aligned to the human way of thinking. We are goal driven. Generates its own experience and experience based learning. Also, why should we rely on RL to achieve agentic behavior? That's because label data is very expensive and time consuming. Also, RL encourages innovation and discovery. So we are not imposing how humans learn explicitly in the RL. And one of the example of it was that in the game of AlphaGo, the move it discovered was not known to a human being. Also, it enables decision making under uncertainty. So not all scenarios will be known to an agent. There would be scenarios where it would be uncertain. So in the agentic AI world, it will enable a decision making under uncertainty. So how agentic AI plus RL enables continuous improvement? We need true autonomous behavior. RL provides the framework for the agent to think under uncertainty given a world model and a long-term goal in mind. So when we talk about a world model or the environment, it could be text-based like a LLM, or it could be simulated like Genie 2 from Google or JPA architecture, which has been proposed by Jan LeCun. Or it could be a real world, for example, the self-driving cars. RL enables the agents to interact in the real world. So examples could be self-driving car, robotic arm in manufacturing. Also, it provides a framework for multi-agent interactions in the form of RL, which could lead to organizational behavior. Now we will talk about a few RL examples in the real world. So what is the relevance of RL in enterprise? It teaches it to take agent to take better decisions over time based on the feedback, just like a good manager would do. Instead of relying on static rules and perfect models, RL uses experimental learning through trial and error while balancing short-term rewards with the long-term outcomes. So for businesses, it offers a way to move beyond static rule-based one-time analytics to dynamic strategies, which can evolve as the environments change or the market shift, or let's say a customer behavior change. So this provides a way to apply RL in different domains. It could be like dynamic pricing strategy in real time, or it could be inventory management system, as well as recommendation engines. It is useful in complex and uncertain business settings where there are external factors which are not under our control, as well as internal factors which are under our control. Let's talk about IT ops or self-healing AI ops. What it does is it continuously monitors infrastructure for signs of stress and takes proactive measures. So in this case, the state could be elements like logs, health status of a component, health stats, uptime, how long it has been, that component has been uptime. The action here could be proactive steps like opening and running a diagnostic or opening a support ticket. The reward structure could be designed so as to penalize infrastructure downtime. And the transition is driven by the infrastructure health based on current concurrency, how many users are accessing or hitting that service, as well as the response availability on the infrastructure side. Let's take another scenario called insurance. So workflow optimization in insurance. When we talk about claim processing, there are multiple stages leading to the final settlement. So start with the intimation of loss. There is an acknowledgement from the insurance company side. There is a validation and triage. Finally, there is an assessment and investigation, wherein underwriter is involved. The underwriter takes a decision. The decision could lead to a denial or acceptance of the payment processing. And finally, there is communication and closure. This would be further followed by a post-processing step like for analytics and compliance. Now, if we define it as a reinforcement learning problem, it could be the decision could be like, should the claim be reimbursed? So yeah, that should be like a decision taken. And if the answer is yes, it moves to the next step. If the answer is no, and the reason for no could be because the policy does not allow, or it could need further probing by a under router. So it might lead to an under router routing scenario. So given a claim, should it be routed to a under router is a decision which is being taken here. Now, under router, they are expensive resources and that they have a limited time and we have to reduce that burden. So in this case, the state design could be, it could involve people in the sense of the demographic data of the person claiming. It can also include his public records, like how many addresses he has changed, whether he has filed for bankruptcy, is there a criminal records, and there are records like LexisNexis. Apologies, there is a typo over here. And then we have the claim details coming in along with the policy details, police report, and past claim behavior. And the action design would be next step to take in a optimized workflow. Reward modeling could be positive reward if the routed claim was found to be fraud, and negative reward if the routed claim was not a fraud. And it led to the resource utilization for the underwriter, or he's spending the man hours. Now let's talk about the call center scenario or workforce scheduling in the call center. So the problem statement is that every morning we have to decide as to how many agents to deploy based on the anticipated call volume for the day. So in this case, the state would be like a current queue length, the available staff members, and the forecasted call arrivals. Action could be staffing level, balancing cost and service quality. Reward structure can penalize longer per customer wait times and high labor expenses, and hence encouraging efficient, which meets the SLA and customer-friendly scheduling. Transitions are driven by the stochastic nature of the call arrivals and agent availability. In the retail dynamic pricing, uh, imagine that one is responsible for setting the price of a product. How do we go about it? So in this case, the state design will capture the critical information like today's inventory level, current price, expected demand based on trends, marketing campaigns, and number of days remaining in the month. The action would be a price to take out of the set of possible values. Reward would be defined by the profit of the day, revenue from sales minus associated costs. Transitions would occur as the customer purchase. They fluctuate in response to the price change, which will affect tomorrow's inventory and potentially influence customer behavior trends. Another example, self-learning robots. Imagine a robots, recycling robots. It has a job of collecting empty soda cans in the office environment. It has a sensor for detecting the cans, an arm, a gripper, which can pick up and place them on a onboard bin. Now it runs on a rechargeable battery, and every step a robot takes leads to exhaustion of the battery. The rover's control system has components which can interpret the sensory information for navigating in terms of a video and controlling the arms and grippers. So these are controls which the robot has. So the task set here is a mobile robot. Its job is collecting empty soda cans in the office. The state design is the current gripper state, distance to the next can, and the battery state. So it will activate. Action design is it can choose to actively search for a can, or it can remain stationary and wait for someone to bring a can, or it can head back to his home base to recharge. Positive reward design could be if the rover secures an empty can, or if it is large and negative, if battery runs down, is exhausted its battery. Let's talk about another scenario, synthetic data generation. So imagine a scenario where my mobile uh, signals is pretty low and I'm not able to make call. So in this scenario, the action to take is to call up the call center. And post that, the next action, logical action would be for the call center agent to provide us with remediation steps and further debugging steps, diagnostic steps. And finally, if I'm satisfying with the call, we can close the call. So these are the actions which could be taken given a state. Now, this problem can be formulated by creating a synthetic data representing a scenario. So each row is a representation of a sensor data, and the action taken is how a call center agent might operate in the given scenario. Now, this synthetic data generation can be expanded to other domains like multi-time chatbot conversations or in queue management. So with that, we will. This is a wrap up with the beginner session. And this should lead to a user having gained a bit understanding of reinforcement learning. Thank you.